Okay, so now today we will cover the 2's complement, addition and subtraction. And last time I told you that whenever we want to perform any operation, we will always be interested in the 2's complement form. So now this is the algorithm for addition, which is called as A plus B. We perform the binary addition on two numbers. Okay, so now these are the algorithms. I will explain this with an example. I will explain this with an example, and this example are very good example, and I will give it with a small example, and then we can do more complex examples following. Okay, assume that we have a 3-bit number. We have a 3-bit number. Okay, so now if we say B2, B1 and B0, we have a 3-bit number. So what are different possible values of these 3-bit number? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, double 1. And now we have 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Its weight is 2 to the power 0 and 2 to the power 1, and its weight is 2 to the power 2 and minus. Assume that it's a, what is the size of n here? What is the size of n? 3. So n is 3 bits, and each particular bit has a weight. So it is because it's a negative number. So it is -4. Its weight is -4 plus 2 and plus 1. Okay, now this will be equal to 0, then 1, then 2, then 3. What about 100? -4. -4 plus 1, -3. -4 plus 2, -4 plus 2 plus 1, -1. Okay, now if you look at here, so we look at the MSB. So we look at the MSB. So now if you look at this MSB, the MSB is 0, it means it's a positive number. And when the MSB is 1, this implies it's a negative number. Okay, now there are a lot of observations here. So now the range of the data for a 3-bit number, the range of the data, can you see the recording? Can you please look at the recording? Oh, it's going on. Okay, good. If you look at here, what is the range of this number from -4 to +3? Got it? Okay, now if we say given an n-bit number, so we can write given an n-bit number, given an n-bit number, the range of the data in the 2's complement form will be from -2 to the power n minus 1 to 2 to the power n minus 1 minus 1 to plus. Okay, now what is n here? 3. So replace n is now 3 here. So it will be -2 to the power 3 minus 1 to 2 to the power 3 minus 1 minus 1 minus 2 to the power 2 to 2 to the power 2 minus 1 minus 4 to plus 3. Now we have proved it. Got it? Because now these are the numbers. These are the decimal representation of the 2's complement form. Any question? Should we proceed? Okay. So now we can, in general, we can say, so any n-bit number, if we have any n-bit number, so we can write this any n-bit number something like this: b0, b1, b2 until what? bn minus 1. And what is the weight of the, so now it is actually, so now we have bn minus 2 and then bn minus 1. Okay, so the weight of this is -2 to the power n minus 1, and then the weight of this is +2 to the power n minus 2, and blah blah blah. What is the weight of this? 2 to the power 2. What is its weight? 2 to the power 1. What is its weight? 2 to the power 0. So in general, if we say, okay, if, so now if we say if bn minus 1 is equal to 1, what does it imply? The most significant bit is 1. What does it imply? bn minus 1, the most significant bit is, So the number is negative, and else, got it? So now for this particular example, what was n here in this particular example? N was 3. So the range was from -4 to +3. If n is equal to 4, -8 to +7. If n is equal to 5, -16 to +15. If n is equal to 6, -32 to +31, and blah blah blah. Okay, so now we have all of these representation. Okay, should I rub this out? Okay, now we do some examples. We do some classical examples. And let's assume if we say, okay, now we are adding two numbers. So what we are adding? We are adding +2 and +1. What is the code for 2? Here, 0 1 0. What is the code for 1? 0 0 1 1 1 0. Okay, now carry in. What is carry in? C in 0. What is carry out? 0. They are same, no overflow. Now if you look at here, what is this? +3. +3 lies within the range, no overflow. +3 lies within the range, no overflow. Got it? Any question? So now what we are doing now? We are adding now +2 and then +3. We are adding +2 and +3. What is the code for +2? 0 1 0. What is the code for +3? 0 1 1. Okay, 1 1 1 0, then 1, this 1, and then 1. Okay, now if you look at here, so if you look at 101, 101 correspond to what? -3. Ideally, what should be the result? Ideally, what should be the result? +5. Does +5 lies within the range? No, because +5 does not lies within the range. This implies that now there is an overflow. So an overflow occurs. Okay, now okay, so what is carry out here now? Carries are same or different? Different. Then overflow. Okay, so overflow. So now we have two for. So now if you look at here, please look at here. Okay, now the MSB of this is 0. If the MSB is 0, positive number or negative number? And if MSB is 1, negative number. So the overflow occurs when we add to positive numbers and the result is negative. So in general, we can say, so now what we are doing, we are adding to positive numbers, okay, and the MSB is 0, and the result is now a negative number, the MSB is 1, so we are adding to positive number and the result is negative. There is an overflow. And we have, now this is a definitely addition, this is an addition. So +2 +3, we are adding these two number and then we get the negative number. Okay, now give another example. Assume another example. Okay, now if we have -4 and -3. So if you want to add -4 and -3, we need to find the 2's complement of -4. What is the 2's complement of -4? 100. What is the 2's complement of -3? 101. We added 1 0 1 1 0 and then 1. Okay, now if you look at here, what is the carry in for this? 0. Same or different? Different. If the carry in and carry out are different, then there is an overflow. So okay, now if you look at here, 0 0 1 is actually equal to what? +1. But ideally, if we add -4 and -3, what should be the result? -7. Does -7 lies within the range? No, because -7 does not lies within the range, then there is an overflow. So now you can use two different methods to identify whether there is an overflow or not. The first method is if it lies within the range. If it lies within the range, no overflow. If it's outside the range, overflow. If the carry in and carry out of the MSB are same, no overflow. If the carry in and carry out of the MSB are different, overflow. Give another, we have another example. Should I rub this off? Okay, I'm rubbing this off and I'm going to get another example. Assume that now we are adding a positive number with a negative number. Assume that we are adding -3 and +2. What is the code for -3? Please help me. 101 and plus 2, 0, 1, 0. When we add it, 1, 1 and 1. Okay, 1, 1, 1, -2 and -1 plus 2, -1. Carry in is what? 0. Carry out is what? 0. Same or different? Same. Overflow or no overflow? No overflow. So 111 is actually the code for what? Got it? So the same thing is true. So okay, now if we now this is the representation. This is the representation in a 3-bit number. Okay, now so should I rub this off? And I will explain the same problem in a 4-bit number. So if we have a 4-bit number instead of a 3-bit number, so in a 4-bit number, how can we write it? B3, then B2, then B1, and then B0. Okay, so we write it something like this. So we say 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. All of them are what? 0. 0, 1, 2, 3, 4, 5, 6, 7, and then 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1. Okay, now if you look at here, what is its weight now? So 2 is for 0, 1, then 2, then 4, and then -8 because MSB. So the MSB is 0. Positive or negative? And MSB is 1. Okay, now we add -1, -8, -8, -8 plus 1, -8 plus 2, -6, -5, then -4, and then you calculate it. -3, then -2, and then -1. Okay, now again the same thing. But in the previous example, in a 3-bit number, this was considered as negative. But now in the 3-bit example, this is considered now as a positive. So please look at the MSB. And we should know that what is the size of the number. Okay, now if you look at here, so what is now the range? See, n is now 4. N is now 4. For n is equal to 3, what was the range? -4 to +3. For n is equal to 4, what is now the range? 8 to +7. If n is equal to 5, -16 to +31, and sorry, +15. And we have the formula. You can use that formula, which I did it in the previous board. Okay, now if you look at here, now we are adding what? We are adding +3 and +4. What is the code for +3? 0, 0, 1, 1 and 0, 1, 0, 0. Can you see the red and the green? What is the red thingy? Carry in of the MSB. So carry in and carry out are same or different? Same. Overflow or no overflow? No overflow. Because 0, 1, 1 is no overflow. No overflow, no problem. Okay, because 3 plus 4 plus 7 plus 7. Can you see? +7 is in the table. When it's the table, no problem. Again, second example. -2, -6. -2. What is the code for -2? 1, 1, 1, 0. What is the code for -6? 1, 0, 1, 0. When you add it, what's the result? -8. -8 is there in the table? Yes. When -8 is there, carry in and carry out are same or different? Same. Overflow or no overflow? Overflow. We discard the carry. In the third example, +6 and -3. +6 and -3. What is the result? +3. Carry in, carry out are same or different? Same. Overflow or no overflow? No overflow. So 0, 0, 1, 1 is a code for +3. You can go to the table. Look in the table. Again, +4, -7. Carry in, carry out are same or different? Same. Overflow or no overflow? No overflow. 1, 1, 0, 1. 1, 1, 0, 1 correspond to 1. 1, 1, 0, 1. -3. And -3 is 9. Any question? Okay, now the same example. So now there are more examples. Now we are adding -3 and -6. -3 and -6. What is the result? -9. Is -9 in the table? No. Then we can directly say, oh, there is an overflow. When there is an overflow, carry in and carry out are same or different? Different. Then there is an overflow. When carry in and carry out are different, there is overflow. Okay. Okay. Now, Talking now in general. So what we are doing, okay, please, please look at here. Please look at here. So minus 3. What is minus 3? Look at the table. 1, 1, 0, 1. And then minus 6. 1, 0, 1, 0. This is 1, this is 1, this is 1, and 1, 1, 0. Same or different? Different. Then overflow. Actually, this is what? 7. Okay, now this is 7 and this is 7. But what should be the ideal answer? What should be the ideal answer? 1, 1, 0, 1. Minus 3 and minus 6. The ideal answer is what? Minus 9. But 9 does not lie within the range, and if it does not lie within the range, then there is an overflow. So there are two methods to detect an overflow. Okay, now please look at, and now we're talking in general. Method number 1, I told you method number 1. I told you method number 2. Now I'm telling you another method. Should I rub this off? Okay. Now, and talk about a general. If given an n bit number, and we are adding to n bit numbers. So let's assume it is a plus b, and these are actually the 2's complement. Okay, so we can say, so we have a n minus 1, a n minus 2, a n minus 3, and blah 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 until a1 and a0, and then we are adding it with bn minus 1, bn minus 2, bn minus 3 until blah 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 b1 and b0. Now when we perform this addition, we got some result. We call this as cn minus 1, cn minus 2, cn minus 3, blah 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 c1 and c0. So when an overflow is 1, okay, please look at this thing. So overflow will be 1. So now we have this table, a n minus 1, b n minus 1, and c n minus 1. So in which bit we are interested? Please, in which bit we are interested? MSB. We are interested in the MSB bit. Okay, now if we say, okay, so it means if we say, please think, if we say if a n minus 1 is 0, what does it imply? A is positive. And then bn1 minus 1 is 0, what does it imply? Positive. And cn minus 1 is 1, negative. And then overflow will be equal to 1. Any question? Got it? So it means when we add, so overflow will be 1 when we add to positive number and the result is 1. Again, another scenario. A n minus 1 is 1, negative. bn minus 1 is 1, negative. And cn minus 1 is 0. And overflow is 1. So overflow will be 1 when we add to positive number and the result is negative. And overflow will be equal to 1 when we add two numbers and we add two negative numbers and the result is positive. So this is another way. Of interpreting this. Okay, now if we say, so now what is the range? What is the range of an n bit number? The range. So now range is minus 2 to the power n minus 1, minus 1 to minus 2 to the power n, 2 to the power n minus 1 minus 1. This is now the range. Got it? Okay, now agreed? Should we proceed? So the overflow will be 1. So if, so we have two conditions. So if the first condition, if a n minus 1 is equal to 0 and b n minus 1 is equal to 0 and c n minus 1 is equal to 1, or what? A n minus 1 is what? 1, and b n minus 1 is what? 1, and c n minus 1 So now this is another. So then in these two scenario, overflow will be equal to 1. Got it? Okay, now I will give you some examples. I will give some examples of the same. So now we are taking, we will doing an example of an 8-bit numbers. Okay, so now should I rub this off? Okay, good. Now we change n. Now we change n. Let's assume that now n is 8. So now we have what? B7, B6, B5, B4, B3, B2, B1, and B0. Got it or not? Not got it? Okay. What is weight? Let's please help me. 1, 2, 4, 8, 16, 32, 4, minus 120, because the same thing. Got it? Okay. Now we want to solve some problem. We want to solve some problem, and now these are the numbers. Assume. Okay. Now, if we have an 8-bit number, so when n is equal to 8, so when n is equal to 8, so the range will be from what? Minus 128 to plus 120. Please think from that perspective. Now we want to perform some computation. Okay. Now we want to perform 100 plus 60. 100 plus 60. What's the result? 160. Overflow or no overflow? Overflow. And then we will prove it. Using a method. Okay. Another example. Okay. Now minus 40 minus 100. Minus 140. Overflow or no overflow? Overflow. And then we will prove it. We'll prove it using the method that we studied. Okay. Now let's assume 40 plus 30. 70. No overflow. Minus 66 plus 100. No overflow. What should be the result? 34. Because it's can't come in the range. Okay. Now, how can we compute 160? 160. Yes, please. How can we compute 160? Okay. Now, how can we and now I'm repeating all of the previous thing. 160. So we can multiply it, divide it by 8, 10, 20, and then 0. Then 8 what? 2 and 4. It is actually what? 2, 4, 0. So if you translate it 0, 0, 0, then 100, and then what? 0, 1, 0. So can you see here? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So you are not interested in it. So okay, now this is 160. Oh no, sorry, we are not interested in 160 because 160 is the result. It is the result. We are not interested in 160. We are interested in what? 100. Okay, now we will use the sum of the weight methods. How can we compute 100? 64 plus 32, 96 plus 4, 100. 0, 0, 0, 0, 0. So it means how can we compute 100? What is 64 plus 32 plus 4 is equal to 100. Any problem? Again, we want to compute 60. What is 60? 32 plus 16, 48. 48 plus 8, 56 plus 4, 60. Got it? Now we calculate this. Now minus 100. We have 100, but we want to calculate minus 100. So minus 100. First, you take the ones complement, Then we add 1. So let takes 1's complement. What is the 1's complement? 1 1 0 1 1 0 0 1. Now this is the 1's complement. Then we add 1. When we add 1, so it will become 1 0 0. Got it? And it is what? Minus 100. Okay, how can we compute it? Please look at here. Okay, now how can we compute it? Minus 128 plus what? Plus 16 plus what? 8 plus what? 4. Okay, 16 plus 8, 24 plus 4, 28, minus 128. The same thing. So now there are different methods. We are also use the ones we converted the 100. We converted 100. We took the 1's complement. Then we add 1, and then it is the 2's complement. And then we use the sum of the weight methods to verify that this number is now minus 100. Any question? Should we proceed? Okay. Now we did it. Now minus 100, minus 40. Minus 40. How can we calculate minus 40? So 40. Let's assume 40. 8 4s are 8 5s are 40, and then 0. So it will 0 0 0, and 5 is 0 1 0. So 1 0 1. Sorry, 1 0 1, and then 0 0. Okay. So now what is this? 32. So we can say plus 40. Okay. How can we calculate plus 40? So plus 40 is what? 32 plus 8, and then I use different methods. Can you see here? The same method. I use the different methods. This is some of the weight methods. Now I want to calculate minus 40. What should we do? 1's complement. 1's complement becomes what? 1 1 0 1 0 1 1, and we add 1. So it becomes 1 0 0. This one is minus 40. And how can we calculate minus 40? So it means minus 40 is actually, so minus 40 is equal to, can you see here? Minus 128 plus 64, which is minus 64, plus 16, minus 48, and plus 8, which is minus 40. Got it? So you're using different methods. We are using a lot of methods. Initially, how did we calculate minus 40? We took the 1's complement, then we add 1. And now we are using the sum of the weight methods to verify that minus 40 is now correct. Got it? We found this 100 and minus 100. Okay, got it. 40. How can 40 is there? 30. How can we calculate 30? 16 plus 8. 24 plus 4. And then 0 0. Okay, this is okay. Now this is a little problem. So now we 1 2 3 4 5 6 7. Now this is 7 actually. So 40 is actually 3 zeros are here. Okay, and then we have 1. Okay, and then 1 and then 0. So what is this? 16 plus 8, 24, 28 plus 2, 30, and then we have 30. 40 is there, and then 100 is there, minus 66. Okay, now you can directly use minus 66. We can. I'm directly using the method. Minus 128 plus 64. Minus 128 plus 64. Minus 64, and to make it minus 66. Minus 2. We don't have minus 2. No, we cannot use this. We cannot use this. Then 0. Okay. Minus 128 plus 32. Minus 96. Minus 96. Minus 16. Minus 80. Minus 80 minus 8. Okay, I think so. This will become a little bit more complicated, but we can do. You can solve it using another method. What was the value? Minus 66. So we can make 66. We can convert this in what? Octal. 2. Okay, 8 2. So 8 2. So now we have 8 2 and 0. What's the code? 0. What's the code? No. Then sorry. 8 1s are 8 and 0. Then this is 102. 102, 010, 000, and then 01, because you know these are 8 bits. So we can, so this is actually, so actually if you look at here, so 102, so 102, so we want to calculate first 60. So what is 60? 0 1 66, 010, 000, and then 10. So plus 66. So plus 66 is what? 64 plus 2. Okay, this was a more easy method. And then minus 66. 1 0 1 1 1 1 0 1, and then we add 1. Got it? So this is minus 66. This is minus 66. So now we did all the calculations, and that's actually I'm now repeating these are all the things like the conversion. I'm just repeating. Okay, now we want to perform the first computation. What is the first computation? 100 plus 60. What is the code for 100? 0 1 1 0 0 1 0 0, and then 60. What is the code for 60? 0 0 1 1 1 1 0 0. Okay, now 0 0 0 1 0 1 0 1 1 1 1 1 1 1 1 0 1 1. Okay, what is carry in for the MSB? 1 is carry out. Same or different? Different. So when we add two positive number, because when we add two positive number, this one is positive, and the result is negative, there is an overflow. Another rule: when the carry in and carry out of the MSB are different, then there is an overflow. The third thing: when we add 100 with 60, it becomes 160. There is overflow. Okay. Now, if you compute this number, please, and this is a very this I will give you another trick. Okay. Now, what is its weight? Minus 128. What is its weight? 32. Minus 128 plus 32. Minus 96. Okay. Now, if you add 96 with 160, if you add 96 with 160, the result will be 256, and it's actually 2 to the power 8. It will always be 256. So there is an overflow. So now this is minus 96, and then there is 160. When we add these two numbers, it will result 250. There is another verification. Okay, now go with another example. We do. So you got it? Okay. Now we do with another example. What is that example? What now we are doing? Yes. What should we now do? So this is, what is this? Plus 100, and what is this? Plus 60. The result is 160, but it does not lie within the range. When it does not lie within an overflow, when we add two positive numbers, the result is negative, there is also an overflow. If the carry in and carry out are different, there is an overflow. When we get this number and we get this 96 with 160, it is 256. Okay. Now take another example. Should I rub this off? What is another example? Yes, please. Please help me. Negative 40. So now we are want to do negative 40 with what? Negative 100. What is the code for negative 40? Negative 40. 1 1 0 1 1 0 0 0. And what's the code for minus 100? 1 0 0 1 1, then 1 0. Okay, if we add it, 0 0 1 0 1 1 1 1 1 0, and then 1. What about carry in? Carry out? 1. Different or same? Overflow. Okay, now when we add to negative number and the result is positive, overflow. Again, so when we add two negative numbers, the result is positive, overflow. Carry in and carry out are different, overflow. Okay, now if you look at here, minus 140. Does minus 140 lies within the range or out of the range? Out of range, overflow. Okay, now we compute this number. Please, we compute this number. 1 2 4 8 16 32 and 64. 64 plus 32, 96 plus 4, 100. 116. We have 116. When we add it to 140, what should be the result? 256. because it is an n bit number and n is 8, it will always be equal to 256. When n is equal to 9, 512. When n is equal to 10, 1024. When n is equal to 11, 2048. N is equal to 12, 4096. N is equal to 13, 8192. You need to remember all these things. Got it? Any question? Should we proceed? Should we proceed? Okay, now, so there are different methods. So if you say minus 140 does not lie within the range, and the range is from minus 128 to plus 128, there is an overflow. Okay, when we add two negative numbers, the result is positive, there is an overflow. With the carry in and carry out of the MSB are different, then there is an overflow. So these are all of the condition for an overflow. So now take this example, 40 plus 30. What is the code for 40? 0 1 0 1 0 0. What is the code for 30? 0 0 0 1 1 1. What is this? 40. And what is this? 30. Where is 30? 0 0 0 1 1 1 2 3 4 5 6 7. Oh, 1 2 3 4 5 6. Okay. Here?
No. At the beginning.
Here?
Other end.
I'm too old, man. You're young. 40. 0 0 1 0 1 3 0. Oh, 3 zeros. Okay, got it. And then 30. 0 0 0 1 1 1 1 0. 0 1 1 0 0 1 0 1 1 0. It is 0. And is same or different? Same. No. No overflow. Got it? Okay, now this is what? 1, 2, 4, 8, 16, 32, and 64. 64 plus 4, 68 plus 2, 70. Lies within the range? Yes. Lies within the range. Carry in and carry out are same or different? Same. Overflow or no overflow? So, okay, when an overflow will occur? When the MSB of the two operands are 0 and the result is 1, or an MSB of the two operand is 1 and the result is 0. If the number does not lie within the range, then yes, overflow. Got it? Okay, now these are the tasks. Please go through all these tasks. So we have a fixed range, overflow. These are all the examples. So now we have binary coded decimals. Okay, which numbers are more natural, binary or decimal? Decimal is more natural. And what about the binary? Who can understand binary? Computer can understand binary. You cannot understand binary. So actually, so now we have different representation of the same data. So binary coded decimal number are more natural to humans. If little compilation is wrong, we use some coding scheme. One such code is called as BCD. We call this as 8421 code. It represents each digit as a 4-bit binary code. I will explain this in an example. Okay, how it works. Now, if you look at here, so each digit, what is the code for 0? 4 zeros. What is the code for 9? 1001. These are the valid code or invalid code? Valid code. Okay. And what about 1010? 1010 is actually 10, which is invalid. So this one 1010, 1011, 1100. These are valid code or invalid code? Invalid code. Okay. So in BCD, each digit is represented by a 4-bit number, 4-bit binary number, and it's very easy to convert. Okay, I will explain this with an example. Should I rub this off? Okay. Now, if you have this BCD representation where each digit, each decimal digit is represented by a 4-bit number. Go to the other slide. What is the code for 234? Can you see? 2. The coding is what? 0010. What is the code for 3? 0011. What is the code for 4? 0100. Similarly, you can go for what is this? 9, 4, 7, 2. Okay, see the color coding. What's this? 8, 6. Okay, so each digit is represented by a binary number, and that binary number is how many bits? 4 bits. Got it? Now, if you look at here, now please look at here. Now we have the decimal representation. Now we have the decimal representation. So 15 is equal to what? 1111. But B15 in BCD is what? 0001, which is the code for what? 1. And okay, so if we have a 3-digit decimal number, if we have a 3-digit decimal number, how many BCD digits are required? 12. If we have a 4-digit decimal number, 16. If we have a 5-digit number, 20. If we have a 6-digit number, 24. Okay, so note that. Okay, so now this is the binary code or BCD code. And what about this code? BCD code. And in this case, 1010 is invalid in BCD. 1010 is invalid in BCD. But 1010 is valid in binary. Got it? Okay, now the gray code. It's very important concept. This gray code is a very important concept. So I will explain this with an example. Okay. Now let's assume we are doing some counting. We are doing some counting. Assume that counting is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. This we are doing some counting. Okay. Now this is actually A0. This one is A1, and this one is A2. We go from 0 to 1. How many bit change? 1 bit change. What is changing? A0. Okay. Now, if we go from 1 to 0, which bit is changing? 2 bits. 2 bit changes. What is changing? A1 and A0. And then we are going from this code to this code, 1 bit. And from this to this, 3 bit change. And then from 0 to here, 1 bit. And from here to here, 2 bit. From here to here, 1 bit. And from here back to 0, 3 bits. Okay, I will explain why gray codes. So in gray codes, the adjacent codes, in gray code, the adjacent code have only a single bit change. But in binary, we do not know. It depends on the code. Okay. So now when we move from 6 to 7, 1 bit change. But when we move from 111 to 000, 3 bit change. When we go from 011, which is 3 to 4, 3 bit change. And in gray code, there is only a single bit change. How? We'll explain this in an example. Okay. Now this is which code? Binary code. Now we have a gray code. 000, then 001. How many bit changes? 1. 011, 1 bit change. Okay. 010, 1 bit change. Okay. 110, 1 bit change. 111, 1 bit change. 101, 1 bit change. 100, 1 bit change. And we go to 1000, 1 bit change. So in gray code, all the adjacent codes have only a single bit change. This is called as the gray code. Okay. So now a binary code. So in a binary code, if we move from one code to another code, so there may be a 1 bit change or a 2 bit change or a 3 bit change in a 3 bit number. Okay. So the consecutive code. But in gray code, the consecutive code have only how many bit changes? 1 bit change. And how can we deduce the? So now this is the binary code. Can you see here? Only 1 bit. Now this is the 4-bit binary number. How many bit changes? 1 here, 1 here, 1 1, and you can go 3, and then 1 1 1 0, and again 0 0. This is a 1 bit change. Any question? Should we proceed? Okay. How do we calculate? How can we generate a code? Yes, please.
How do you know which bit is the one?
Which one?
How do you know which bit is the one supposed to change?
It can be any, but there can be only 1 bit change.
Okay, so there can, instead of going from 011.
So from no, I'm talking about the consecutive code, not from here to here. Only the consecutive. We are only interested in the consecutive. We are here and here, not about like we are not doing a big jump. We are only doing the counting. Yes, please.
How do we know the representation of the number in gray code?
I will tell you. There are different methods, and we can do it. We can do it. Okay. Now, what's the representation? Can you see here? Okay. Now we have a 4-bit binary number. We have a 4-bit binary number. We start from 0 0 0 0 and then 0 0 0 1. Whenever we generate, so it's the code for 0 and this is 1. Okay. Now, whenever we want to generate a code, we reverse it. So okay, what will we write? 0 0 0 1 and then 0 0 0 0. Okay. So now what should be the next code? 0 0 0 1 and then 0 0 0 0. Got it? Replicate the pattern in reverse order. We replicate the pattern in reverse order. When we do it, so then when we replicate the pattern and then we change the second most bit, this one. So we'll change this bit. So we'll replace this the second bit with 0 to what? 1. Got it? And then again we replicate the same pattern. We replicate the same pattern. What should be the pattern? Yes, please. 0, then again. Replicate the pattern in reverse order. And then what should we do? Change the third bit. Got it? And then again, what should we do? Now we have an 8-bit number. Replicate. What should we do first? 0 1 0 0, 0 1 0 1 in the reverse order. What should we do now? And if you look at here, for each consecutive, so okay, now this is a consecutive number. 1 bit change, 1 bit change, 1 bit change, 1 bit change, and you can verify it. Okay, and then we say 1 bit change, 1 bit change, and then there is a consecutive 1 bit change. Okay, now, and you can, yes, please. Got it? We replicate reverse order. It will be 0 0 0 1 and 0 0 0 0. Got it? Then we change this bit. This bit. It will become 1 and it will become 1. Got it? Then we replicate pattern. First we write 0 0 1 0, 0 0 1 1 0. Got it? Replicate. No. Yes, this is 0, this is 1, this is 2, this is 3. Got it? Then replicate in reverse order. 0 0 1 0. Then got it? And then change the third bit. Got it? And then you replicate in what? Reverse order. What should we write first? 0 1 0 0, then 0 1, then 0 1 1 1 in reverse order. And then replicate, invert what? The last bit. Got it? That's how it's generated. Okay, now this is the way that, okay, now we can replicate the same concept. We can use the same concept to generate a 5-bit number. So we can say 0 0 0 0 and then 0 0 0 1 and then reverse order, and then the first bit, replicate the second bit, invert the second bit, then invert the third bit, then invert the fourth bit, and then invert the fifth bit. Got it? The same concept. So binary given a binary number, how can we generate the gray code? Okay, now this is very important. This is very important. And this gray code is very important. We will do this gray code in logic minimization in a lot of techniques. We will use this gray code. If this concept is very much important, it will be covered, and especially the conversion of a number into binary is also very important. Okay, now if you look at here, we want to convert a number. This is a black box. It's a black box, and given a number which is actually what? What is the size of the number? 1 2 3 4 5. What is the input? Binary. So we say B4, B3, B2, B1, and B0. What is the size? What is n here? N is 5. The output is a gray code. So B stands for what? Binary. And G stands for what? Gray. G4, G3, G2, G1, and G0. Okay, now what is this? G what? G5. Okay, how can we get the gray code? We replicate the most significant bit. So it means that now, what is G4 now? B4. G4 is now B4. So now this is B4 and now this is G4. If it is 0, we will replicate 0. If this is 1, we will replicate 1. And then we get the other bit. How can we get G3, please? How can we get G3? B4, not we use exclusive OR. This is exclusive OR. B3. What is an exclusive OR? Let's assume if we say then we are 0 0, then we are 0 1. This is 1 0. This is 1 1. So 0 0 means 0 0 1 1. 1 1 0 is 1 and 1 1 is 0. Got it? So we get B4 exclusive OR B3. Okay. How can we get G2? Yes, please. G2. B3. How can we get G1? B2 exclusive OR. We call this exclusive OR. Okay, B1. And then how can we get G0? Got it? Okay, now in this particular example, what is n here? Please. N is equal to 5 and n is also is equal to 5 and we generalize it. Now we generalize it. So what is, can you see here, what is Gn minus 1? The most significant bit, Gn minus 1. What is Gn minus 1? Bn minus, because we replicate the most significant bit. Gn minus 1 is what? Bn minus 1. Got it? Okay, now what is Gn minus 2? Bn minus 1 exclusive or Bn minus 2 and blah blah blah. What is Gn minus 3? And blah 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 until we have now. Okay, now we want to calculate G1. G1 is equal to B2 exclusive or B1 and G0 is equal to B1 exclusive or B0. Got it? Okay, now if you look at here, so this is for the most significant bit. Okay, now what is I here? What is I here? Yes, please. What is I here? 2. What is I here? 3. What is I here? Okay, I is equal to 2. I is equal to 2. So can we write it like this? What is Gn minus 1? Gn minus I. What is Gn minus I? Gn minus I is equal to Bn minus I minus 1 exclusive or now Gn minus 1. So Gn minus I is equal to what? B n minus I. This is n minus I. Okay, and then Bn minus I plus 1. Got it? So now this is a generalized formula. This now is generalized formula. You can have a generalized formula. Got it? So now we have the gray code for this. What about this? What we are doing? 1 plus 0, 1. 0 plus 1, 1. 1 plus 1, 0. And 1 plus 0, 1. So what is the input? 1 0, 1 1 0. Binary code or gray code? How do you know it's binary? Base 2. How do you know it's gray? Got it? So now given a 5-bit binary number, we have converted into a 5-bit gray code. Got it? Okay. Now we want to transform back from the gray code to binary code. Got it? Okay. Now I'm rubbing this off. So now we have again n is equal to 5. What should be now the input? G what? G4, G3, G2, G1 and G0. What is now the output? B4, B3, B2, B1 and B0. And in general, how can we write it in general? We can start from Gn minus 1, Gn minus 2 and blah 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 until we go 0. So how we transform this in retain the most significant bit, the same thing, retain the same bit. So now in this case, in this particular example, what is now B4? No, it may be 1 or it may be 0, doesn't matter. G4 is what? G4. So the input is the gray code and we retain the MSB. When we retain the MSB, so actually B4 is equal to G4. Got it? Now, and now if you look at here, what is this? B4. So how can we get B3? Help me, help me. B4 exclusive your G3. Got it? Then how can we get B2? What about B1? What about B0? G what? 0. So in general, how can we write? What is Bn minus 1? Gn minus 1. What is Bn minus 2? Now what is, this is n minus 1. What is n here? The weight. Okay, this is 5. This is what? 4. This is 3. This is 2. This is 1. I will call it n. So Bn minus 2. What? How should we write it? Bn minus 1. This is your what? N minus 2. Got it? And then Bn minus 3 is equal to what? And blah blah blah. And now this is B1 and B0. Got it? So we can write it something like this. So this is actually I. So what is Bn minus I? Bn minus I is equal to Bn minus I, n minus I plus 1 minus 2 plus 1 is minus 1. Exclusive or what? G I. Got it? So now this is a generalized expression. So now we can also derive the generalized expression from this specific example. So what we do? So now we replicate this, and then one exclusive or 1 0. 1 exclusive or 1 is 0. Then 0 exclusive or 0 0. And then 0 exclusive or 1 1. And then 1 exclusive or 1 0. So now we have the gray code is your input code and the binary code is your output code. Okay. Now this is the gray code. What is the gray code? 1 1 0 1 1. And what is the binary code? 1 0 0 1 0. Now error detection code. Okay, why error detection codes are important? Now let's assume if we want to send some data. If we want to send some data from the source to the destination, and we transmit this signal, on a transmission line. And maybe there are some environmental noises, and because of this environmental noises, some of the bits may change. Assume that now we have a transmission and a receiver. So assume that we have a transmission and a receiver, for instance. We send some data, and this data is 0 1 1 0, And when we receive this data and it becomes 0, 1, 0, 1, what's the problem now? There is an error. Error in which bit? The third bit. So actually, why error correcting codes are important? The error correcting codes can be used to identify the errors within the data. How? Let's see. Okay, now we have some data bits and now we have some code bits. We have some data bits and now we have some code bits. Assume that we have a 3-bit data. We have a 3-bit data. What is now the data? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. These are called as data bits. What is n here? N is 3 because these are 3 bits. And now these are the data bits. Now we have other bits which is called as the code bit. This code bits is a function of the data bits. And assume that we are using some parity bits. And the parity bits we say that odd parity. We say that the number of the ones in the complete code is odd. Okay. So now 0, 0, 0, odd or even? How many ones? 0. Odd or even? Even. To make it odd, we put what? 1. 0, 0, 1. How many number of ones? Is it odd or even? Odd. What should be the code bit? 0. Okay. 0 and 0. What should be the code bit now? 0. Because we want to make it odd. Okay. So now if you look at here, how many ones? Number of ones? How many number of ones? 1. How many number of ones? 1. How many number of ones? 1. 0, 1, 1. 2. To make it odd, how many number of ones? 1, 0, 0. Odd or even? Odd. To make it even or to make it odd? 1, 0, 1. To make it odd? 3. So actually this is called, okay, now if you look at here, now we send some data. We send some data. Okay, 0, 0, 0, 1 is a valid code or invalid code? Okay, now if you look at here, if you combine this data bits and the code bits, so what is now the total size? 4 bits. How many combinations are there? 16. There are 16 combinations. Out of these 16 combinations, 8 combinations are valid or invalid? Valid. And other 8 combinations are invalid. I will explain this in an example. Okay, now if you look at here, let's assume. So if we say 1, 1, 0, 0, 0, valid code or invalid code? Valid code. Where is this? Now if you say 1, 0, 1, 0, valid code or invalid code? Why it is invalid? Because it's even. So that's the reason. So if you say, so when the receiver receives 1, 0, 0, it means now the data is correct. And when the receiver receives 1, 0, 1, 0, it means that the data is incorrect. Okay. Okay. Now this odd parity can detect a single bit error or multi-bit errors. It can only detect single bit error. Why? I will explain this in an example. Assume that now we say that 0, it is 0, 1, 0, 0. Valid code or invalid code? Valid code. Assume that there is a single error and the error occurs in this bit. This is an error here. So 0, when we receive 1, 1 and 0. Invalid code. When it's invalid code, it means okay, there is some error. But we do not know in which bit it occurs. Maybe it occur in this bit or is this. So it may ask the transmitter to retransmit the data. Got it? So now, okay, now assume that we have this 0. Now we have this 0, 1, 0, 0. Valid or invalid? Valid. And there are 2 bit changes. There are 2 bit changes. This changes to 1, this changes to 1, 1 and 0. Valid or invalid? It's still valid, but it cannot detect. So the parity bit can detect a single bit error or multi-bit errors. Single bit error. Got it? So now this is an example of the single bit error. So now we have an error code. Okay. Now if you look at here, now please 0110. It's a 4-bit data. 4-bit data word, and the code bit is shown in which color? The blue color. Okay. 011. To make it odd, we will put what? 1. 1 0. Got it? So this is called as a row-wise parity. This is called as a row-wise parity. So now can you see here? This is called as the row-wise parity. And now this one is called as the column-wise parity. Can you see here how many ones in this column? 3. We put a 0 here. Okay. Now 1 1. How many? 2. Make it 1. So when we send this data, we send the complete data, so it will calculate the column-wise parity and the row-wise parity, and if there is a change, so it can detect some errors in the code. Okay, and then you say, okay, whether the data is correct or whether the data is incorrect. Okay, when the data will be correct? So we should have always the odd number. Okay, now explain this with an example. Okay, now if we have 0 1 1, if we have 0 1 1 and 1, how many ones? 4 ones, and then it means it will detect the error, and then it may ask the transmitter to do what? To retransmit the data. So when we send some data, we have the code word and we have the data words, and we derive these code words based on counting the number of ones in the data word. If the number of ones in the data words are even, the code word is what? 1. And if the number of ones in the data are odd, the code word is 0. Got it? Okay. And then at the receiver end, so it will calculate it will have both the code words and the data words. Okay. And then it will count the total number of ones. If the total number of ones are odd, valid code or invalid code? Valid code. If the number of ones are even, invalid. And then if it is invalid, it may ask the retransmitter to do what? Retransmit the data. Any question? Should we proceed? Okay. Now the ASCII character code. Okay. So now we have different data, and different data has different representation. We have a lot of representation. We have the binary data. We have an unsigned number. Then we have signed number. Oh, in signed number we have sign in magnitude. Then we have ones complement. Then we have twos complement. Then we have the gray code. Then we have BCD code. Okay, and now we also have the ASCII character code. So every data, if you look at the computer data is always surrounding by, okay, the chunks of 1 and 0. But what type of data is this? It depends on the code. So now we have the ASCII code. The ASCII code is used for different type of characters within your keyboard. Okay, what are these codes? If you look at here, so the most common key is ASCII, American National Standard Code for Information Interchange. So if you look at the ASCII table, so okay, so if you look at here, the MSB is in the row and the LSBs are in the column. What is the size of the total data? 7 bits. 7. So it means it is B6, B5, B4, B3, B2, B1 and B0. Okay, now if you look at here, so now now what is the code for A? The code for A is 1100001. Okay, 1100001. Actually, and this code is actually 97. Why 97? 64 plus 32. 96 plus 1. 97. Got it? So now this is the ASCII value of A. This is the ASCII value of A, and the ASCII value of A in decimal is 97. Okay, how does we calculate it decimal? Because this is the most significant bit. The most significant bit is what? 64. The next 32, and then plus 1. Got it? Okay, now these are, if you look at here, these are called as the graphical code. All these combinations are the graphical codes. Like you can see something, the graphical code, you can see that data. Let's say, what are the graphical codes? A, you can see it on the monitor. B, you can see it on the monitor. These are the graphical codes. And these are the control codes. You cannot see them. just like a farishta. You know, can you see? Farishta exists. Farishta exists, but you cannot see it. But you can see me because so now I'm maybe the graphical code and the farishta, you cannot see this, you cannot see null, you cannot see enter. So this is called as the farishta, we can say angel. So angel, okay, now these are the control code. You don't see them, but it has a code. Let's assume if we say null, there is a null, escape, maybe there is a null, and these are the delete character, carriage return. Carriage return is for what? Enter. What is CR? Carriage return. When you press the enter button, it will generate a code. Got it? So every digit which is even not visible, but it has a code. So these are called as what code? Control code. Control codes. Within ASCII, okay, now we have fruit, we have fruits, then we can have apple, we can have banana. So now we have the ASCII code. Within ASCII code, we can have the graphical codes, graphical character, then the control codes. And if you then we have alphabetic code within the graphical codes, we can further classify the graphical codes into the alphabetical code. The capital letters. What is the code for A? A is 65. 65. 65 is what? 64 plus 1. So it is actually 100. 64 and then 001 plus 1, 65. Okay. Now the code for B is 66. 64 plus 2, it's 010. Got it? So now these are the alphabetic code which represent both the positive number, and because for the computer it differentiates between, okay, if we say, okay, now what is this? Ali and Ali. If you look at it, both are same, but for computer this A is different from this. Got it? So that's so it means that the capital letter and the small letter has different codes. And now these are the numeric codes. What are the numeric codes? 0, 1, 2, 3, 4, 5, 6, 9. Okay, now this zero is actually a character. It is when it is treated as a character, so its code is 011. Can you see here? 011000. So 32 plus 8, 40. So the ASCII code for 0 is what? 40. When 0 is treated as a character, its code is 40. But when 0 is treated as a decimal, its code is 0000. When 1 is treated as a character, its code is what? 41. But when it's treated as a binary number, 000001. Got it? So now these are different data. We have different representation of the data. We have different notion of the data. So if you say, so that this is the ASCII table, okay? And now what we say, let's assume if we say, okay, now it's very important for you, and this is a very important concept. If we say int A is equal to 65, character CH is equal to 65, and we say C out A, what will it display? 65. But if we say C out CH, it will display A. So now we have different data, but we have different representation of the, both has the code of 65, but both has a different meaning. It's all for today. Thank you very much. If you have any questions,